With this definition in mind, let's look at some examples. To start with, let's recall some monoidal categories V that we can enrich over. Our first example of a monoidal category will be set with the Cartesian product and the singleton set as a monoidal unit. And we know that this is a closed symmetric monoidal category. And the right adjoint to taking the product with B on the left is the covariant Hom functor represented by B. Our second example will be the category of categories with the usual product of categories and the one element discrete category as the monoidal unit. And this is also a closed symmetric monoidal category. And in this case, taking a product with B on the left has as right adjoint the functor category from B to some other object. Third, I'm going to define a preorder. So we let B be the preorder generated by the set false and true, and the relation false is less than or equal to true. Because B is a preorder, we also have reflexivity, so B will additionally include the relation false less than or equal to false and true less than or equal to true. Then there exists a monoidal category Bool, which has as objects the elements of B, and as morphisms the relations that are satisfied in B. So it'll have an arrow between false and false, which will be the identity. It'll have an arrow between true and true, which is the identity, and also an arrow between false and true. And now we define a monoidal product on this preorder regarded as a category, which is AND. So that's the logical AND. This means that false and false is false, false and true is false, and true is true. And this has as monoidal unit true. Because if we take true and false, we get back false, and if we take true and true, we get back true. In fact, this is a closed symmetric monoidal category. Why is that? Well, we have, for example, that true and false is equal to false and true, since the operation AND is symmetric. But this holds for any truth values that we would insert there. That is, the operation AND is symmetric. Moreover, we don't have to check the commutativity of the diagrams involved, because this is actually not only a closed symmetric monoidal category, it's also strict. So the commutativity of the diagrams involved is trivial, so we just have to check the axioms. So we know that this operation AND is symmetric. We have the unit, so if we have any truth value A, if we take the operation with it and true, we get back A. The other way around also works. This is also a consequence of symmetry. And finally, we need to check that AND is associative, but this is the case because A and B and C is equal to A and B and C. So this shows that it's a strict symmetric monoidal category. Finally, we need to check that it's closed. What does this mean? Well, it means that the operation taking and with A on the left has a right adjoint, but because we're in a preorder, having a right adjoint translates to the following condition. We have that A and B is less than C if and only if A is less than, and here comes the operation that we're trying to define, so this would be the internal Hom of B and C. We saw a similar example to this when we were talking about the preorder of the subsets of a given set, so that's the power set preorder, and in this case we have a similar solution, namely that we need to take implication to be the internal Hom, and implication is logically not B or C. One can easily verify this by checking cases, so suppose that C is false, then because A and B is less than C, A and B together has to be false, which means that A is false or B is false. Now in the first case, if A is false, then certainly it's less than anything else. In particular, it's less than not B or C. And if B is false, then not B is true, which means that not B or C is true, and in that case, A is less than or equal to true in any case as well. So if C is false, then we're good. On the other hand, if C is equal to true, then we don't know anything about the left-hand side. However, in that case, not B or C will always be true, and so it's always going to be greater or equal to A. So this shows that the implication from the left to the right holds. Conversely, suppose that the expression on the right holds. Now A could be false, in which case we don't know anything about the right-hand side, but in that case A and B is false, so it's certainly going to be less than or equal to C. So in this case we're good, and if A is true, then we know that not B or C has to be true, because not B or C is greater than A. If not B or C is true, then we have two options. Either not B is true, in which case B is false, and then that means that A and B is false, and then it's less than or equal to any C. So that case is good. On the other hand, if C is true, then A and B will be less than or equal to C in any case, because C is true and thus greater than any element of either true or false. So this shows that also the other direction holds. In summary, we've seen that Bool is a strict closed symmetric monoidal category where taking and with B on the right is left adjoint to not B or dash. At this point I noticed that I made a mistake in the first two examples, so I put B on the wrong side of the product in both cases. So we have, in reality, the functor we're looking for is dash cross B in both cases, not B cross dash. For example, we have Hom A cross B, C being isomorphic to Hom A, Hom BC. So we have to have B on the right here. Our fourth example is similar to the third. So we let R plus bar denote the extended non-negative real numbers, and we want to have these under the ordering greater or equal to. For example, 3 is greater or equal to 2, and infinity is greater or equal to any real number. We now define a monoidal category called cost, which is equal to the extended non-negative real numbers under this ordering relationship greater than or equal to. And we have a monoidal product, which is addition, and the unit with respect to this product is 0. And this is a strict, closed, symmetric monoidal category. The fact that this is a symmetric monoidal category follows from the fact that addition is associative and commutative, and that 0 is the unit with respect to addition. Because all of these relations hold up to equality, this means that cost is in fact a strict symmetric monoidal category. To show that it's closed, we have to give a right adjoint to adding an element on the right. So we want dash plus a being left adjoint to some operation involving a. Again, because this is a preorder, we can translate this to the condition that b plus a be greater than or equal to c if and only if b is greater or equal to, and here comes the operation between a and c. Now it turns out that the right operation to take is the maximum between 0 and c minus a. This is simply the case because b plus a is greater or equal to than c if and only if a is greater or equal to c minus b. However, now we have the problem that c minus b might not be an element of the extended real numbers. Luckily, the above relation is also the case if and only if we have that the maximum of 0 and a is greater or equal to the maximum of 0 and c minus b, but the maximum of 0 and a is just a because a is a non-negative real number, or infinity, and so we get that this is the case if and only if the maximum a is greater or equal to the maximum of 0 and c minus b. And the latter is going to be an element of the set R plus bar. Our final example is going to be more algebraic in nature again. So we'll take the abelian groups, so that's the category of abelian groups, together with the tensor product of abelian groups, and z as the monoidal unit, and this is a closed symmetric monoidal category where taking the tensor product dash tensor b is left adjoint to Hom b dash. This works out because the Hom set of two abelian groups is again an abelian group. Okay, so now that we've reminded ourselves of 5 monoidal categories that have nice properties, we can see what the corresponding enriched categories would be if we take any of these to be V in the definition of a V category. Let's start out by thinking about what set categories are. If we go through the definition, we see that we have a collection of objects, and for each pair of objects, we have a Hom object, which in this case is a set. Moreover, we have a composition map, MABC, which is now a map in sets, so it goes between the Hom set of BC cross Hom AB to Hom AC. And finally, we have an identity for each object, which is a map from the monoidal unit, which in our case is the singleton set, to Hom AA. And these maps are required to satisfy the commutativity of the 2 diagrams that we need for specifying an enriched category. But as we saw in the introduction to this video, those diagrams are precisely the diagrams we need to commute if we're displaying the axioms of a normal category in terms of these maps. So in fact, set categories are just small categories. They're locally small because we require a set of arrows between any 2 objects, and in the definition of an enriched category, I also required there to be a set of objects for an enriched category, so that means that these categories are just small categories. This is good because we recover the usual definition of a category as a special case of the enriched category. Next, let's think about what a cat category is. In this case, the HOM objects are categories, and we have a functor that specifies composition. If we call our cat category D, then we have in the notation from before, this is D, B, C, so this is the category, that's the HOM object of B and C. Now, the tensor product is just the product of categories, so we get DBC cross DAB to DAC. And this composition is now a functor from the product of these two categories to the third category. So this specifies a bifunctor. And finally, our identities are maps from the one object category into the HOM object of A and A, that's DAA, and we know how the one object discrete category looks, so it's going to pick out some object of this category DAA and the identity morphism. Finally, these maps need to require the two diagrams, so that's associativity and unitality, and this concludes what we need for a cat category. Now, one example of a cat category is the category of small categories itself. So cat is itself a cat category, and this is because we have objects, and between any two objects we have a category of morphisms. That's because functors between two objects themselves form a category, namely the functor category. In general, cat-enriched categories are called strict two categories. And we've already seen what data and we need to specify and what properties these data need to fulfill to be a strict two category. I'm noticing that there's some size issues with the definition I gave that requires the objects of an enriched category to be a set, but I'm just going to ignore this for the moment. So in general, set categories would be locally small categories if we allow some arbitrary collection of objects in our enriched category, and in this case, the category of small categories, cat, would actually be a cat category if we allow some arbitrary collection of objects. Now, what's interesting about both of these cases is that we have enrichment of a category over itself. So to be more particular about what I mean, set, the category of sets, is a set category. This means that we can view set as a category as a enriched category that's enriched over itself. Similarly, cat is a cat category. So we can view cat as a category enriched over itself. In fact, whenever we have a symmetric closed monoidal category, we can endow that category with an enrichment over itself. So the special cases that we're looking at here is where we have a closed symmetric monoidal category of set with a Cartesian product, or a closed symmetric monoidal category of cat with a product of categories. And possibly in a future video, I'll talk more specifically about how this works in the general case. Let's turn to what a Bool category would be. So let's call this Bool category B, and for every pair of objects we have some HOM object BAB, which is an element of the preorder B. And we recall that this is false or true. This means that for any pair of objects, the HOM object between it is either just false or true. Moreover, we have to have some composition map that is a map in the symmetric closed monoidal category Bool that goes from B, BC, And now we use the product in that category, so the tensor, which is and b a b, and this is a map in that category, and since it's a preorder, this is going to be less than or equal to BAC. What is this telling us? Well, really, because these operations are so restrictive, this is more imposing a condition on the way that our Boole category is structured rather than being some sort of composition law. So it's saying that if we have objects A, B, and C, then the Hom object between A and B, so I'll draw this as an arrow, and B and C, they have to have a specific relation, namely that if we take the value of and of both of those objects, then this has to be less than or equal to the Hom object between A and C. So let's see what this means. For example, if the first arrow between A and B is true, and the second arrow is false, then this means that taking true and false, which is just equal to false, needs to be less than or equal to whatever is on whatever value is in the arrow of between A and C. Now in this case, this doesn't place any restrictions on this value. So we could have a false here, or we could also have true, because this inequality isn't placing any restrictions. The same is true if both the arrows between A and B and the arrows between B and C are false. Then too, this inequality isn't placing any restriction on what the value of the arrow between A and C needs to be. However, in the case where both arrows are true, we have that this expression on the left is true, and this needs to be less than or equal to the expression on the right, but the only way that that's possible is if the expression on the right is also true. So in that case, we already know what the value between A and C needs to be. In other words, this relation, which holds for all triples of objects, is saying that if we have true between A and B and true between B and C, then we also need to have true between A and C. So in fact, this is a type of transitivity that we're enforcing on the Boole category by the fact that we have this relation for any triple of objects. The second ingredient we need is for every object A, we need an identity, which in this case is a map from true, which is the monoidal unit, to the Hom object on A. But this is saying that true is less than or equal to the Hom object on A, which means that this has to always be true. So in fact, the arrows that go between any object and itself have value true. Now we can reframe these data in a different way, namely, if we have some arrow true between A and B, we can write that A is related to B. And if we have an arrow false between A and B, then A is not related to B. With this interpretation, what are these requirements saying? Well, we have that either A is related to B or A is not related to B by the fact that the values of these arrows are either true or false. Moreover, the composition requirement is saying that if B is related to C and A is related to B, then we have that A is related to C. And finally, we have that A is related to A for all A. Now these are precisely the axioms for a preorder, so in fact, Boole categories are just preorders. If we wanted to be a bit more precise, we could say that there's an equivalence of categories between the category of Bool categories and the category of preorders. But so far we haven't defined enough structure yet with enriched categories to know that enriched categories that are enriched over some monoidal category themselves form a category. All right, but this is nonetheless interesting because it means that Bool categories are preorders, but Bool was itself a preorder. So in fact, Bool categories are enriched over themselves as well. Thus, this is again a manifestation of the fact that we can enrich a closed symmetric monoidal category over itself. Let's turn to the example of cost categories. What are the data that we need for a cost category? Well, we need for any pair of objects, we need a Hom object. And what is this? Well, it's just an element of the extended non-negative real numbers. So it's some number between 0 and including infinity. Next, we also need a composition law, which in this case, again, because the extended real numbers is a preorder, takes a simple form of a requirement that we need to satisfy. For convenience, let's call this cost category B. Now, the composition relation is saying that BC plus because this is the tensor product in cost, plus BAB should be greater or equal than. This is because arrows in cost are greater or equal than, should be greater or equal than BAC. Finally, we have an identity for each object, which is a map from 0, which is the monoidal unit, to the Hom object BAA, but this map takes the form of a greater or equals than. Because we're only dealing with non-negative numbers, we can deduce immediately that this means that the Hom object between any object and itself needs to be 0. Finally, because cost is strict, we don't have any additional requirements that are imposed by the commutativity of the diagrams. Okay, so let's think about what this is saying. So we have some objects, again, A, B, and C, and between any two objects, we have some value, which is an extended non-negative real number. So we could have, for example, 3 between A and B, we could have 5 between B and C, and then we could have some other value between A and C. Of course, we also have values between every object in itself, which the identity requirement is saying have to be 0. Now, if we look at this relationship between Hom objects, we have that the Hom object between A and C has to be less than or equal to the sum of the Hom objects between A and B and C. For example, a valid Hom object between A and C would be 7, because 7 is less than or equal to 8, which is the sum of the other two arrows. In fact, this thing up here is basically the triangle inequality. And if we interpret the Hom objects as distances, then cost categories are something like a generalized notion of a metric space. So as a reminder, in a metric space that takes extended values, so sometimes called an extended metric space, we have a distance function which goes from, let's call the metric space M. So we have a distance function that goes from M cross M and takes values in the non-negative extended real numbers, and that satisfies some axioms. So the first axiom that a extended metric space needs to satisfy is that the distance is symmetric. Second, we need that the distance between points is 0 if and only if the points are the same point. And third, we have the triangle inequality, which is saying that the distance between x and y plus the distance between y and z is greater or equal than the distance between x and z. Now, if we compare the axioms that are required of an extended metric space with the requirements we have in a cost category, we see that there are some points of agreement. Most significantly, we have an assignment of values in the extended real numbers that satisfies the triangle inequality. So C is a check, and our distance function is just the assignment of Hom objects. We also have that, which I'll write as B prime, the distance between any object and itself is 0. So we have one direction of this implication holding in a cost category. However, the other direction does not need to hold. So this direction is not necessarily fulfilled in a cost category, and also symmetry does not necessarily have to be fulfilled in a cost category. This means that every extended metric space is in particular a cost category, albeit one that satisfies some further requirements. So we can see cost categories as a generalization of extended metric spaces. This generalization may be useful because we might not always want our distance function to be symmetric. For example, if we have some village A that's on top of a mountain and some village B in the valley, then we might want to have the distance function giving us the time it takes to get from A to B or from B to A. And of course, if we go from B to A, we have to climb up the mountain, which generally takes longer than if we were to climb down the mountain. So in this case, we might not want to have a symmetric distance function. Similarly, we might not always want to have that if the distance between two points is 0, then those points have to be the same point. Of course, if we have less axioms, then we also have less proof power for these objects. But it's nonetheless interesting to see that the idea of an enriched category subsumes the idea of an extended metric space. Last but not least, let's look at AB categories. And instead of looking at a general AB category, I want R to be a one-object AB category. Let's see what this means. So I'm going to denote the one object we have in R by star. So we have an object star, and then we need to have a Hom object for this object. So we just need R star star, since this is the only pair of objects we have in our category. Further, we need just a single composition map, which I'll just denote M, that goes from R star star tensor, and this tensor product of abelian groups, to R star star, like so. And finally, we need the identity on star, which is going to be a group homomorphism from Z to R star star. First, let's observe that group homomorphisms from Z to any abelian group are basically determined by where the element 1 in Z is mapped. We know that 0 has to be mapped to the identity of the abelian group in any case, but the image of 1 completely determines what the homomorphism is going to be. So let's denote the image under 1 by 1R. Next, let's also observe that we have a map from the product, that's the direct product of abelian groups, to the tensor product. And this map maps the pair A comma B to the elementary tensor A tensor B. Moreover, the composition of this map from the product to the tensor product and the map M gives us a composite map from the product of these Hom objects to a single copy of the Hom object. And this will map a pair AB to M of A tensor B. For convenience, I'll just denote this operation as A times MB. Now let's see what the axioms for an enriched category are telling us about this operation. First off, we note that if we have elements A and B in R star star, then because R star star is an abelian group, we have that we can add these elements. So this implies we have an element A plus B in R star star, and moreover, we have all the axioms for an abelian group satisfied with respect to this operation. Moreover, if we look at elements A, B, and C, then we can map A and B plus C, can map this under the map from the product to the tensor product to A tensor B plus C, which is the same as A tensor B plus A tensor C, where we're using the abelian group structure of the tensor product of abelian groups. Finally, we can map this with M, which, because it's a map in the category of abelian groups, is in particular a group homomorphism. So if we map this, we get M A tensor B plus A tensor C, which by the group homomorphism property is M A tensor B plus M A tensor C. And using our other notation, this is just A times MB plus A times MC. On the other hand, if we would have not expanded this element into two summands, we would have gotten that this is equal to M A tensor B plus C, which using our other notation is A times M B plus C. But because these elements are equal in the tensor product, their image needs to be equal. So in fact, we have that, I'll write it out more nicely, A times M B plus C is equal to A times M B plus A times M C. This means that this multiplication that I've defined using this map M distributes over addition in the abelian group R star star. Finally, let's see what unitality means. If we're given some A in R star star, then we have the following. We have that R tensor Z mapping with the identity tensor, the identity on star to R star star tensor R star star. And now using the composition map is the same as if we just used the right associator. Let's again look at a pair of objects. So we're mapping R star star cross Z into this tensor product and seeing what the image is going to be. So we take some element A in R star star and we look at 1 in Z. And now this is mapped under this map into the tensor product to A tensor 1. Now under identity cross the identity morphism on star, this is mapped to A tensor 1R. And finally, under the composition map, this is mapped to M A tensor 1R. On the other hand, we could have taken the right associator, and this gives us A. This is because the isomorphism between abelian groups. So if G is some abelian group and we have its tensor product with Z, there's an isomorphism that goes to Z. And what does it do? Well, it takes some element A in G and some element N in Z, and it maps that element to N times A, where this times is addition of A N times with itself. In this case, we're mapping A tensor 1 to 1 times A, which is A. Now, the commutativity of this diagram is stating that A is equal to the image under the composition of A tensor 1R, and in our other notation, A tensor 1R, or under this composition, is equal to A times M 1R. So the second relation that we have for this one object AB category is that A is equal to A times M 1R. Now we have a second diagram that goes in the other direction that will give us the relation that A is equal to 1R times MA. Finally, I forgot to mention before, by symmetry, we also have the distributive property in the other order, so it's also the case that A plus B times MC is equal to A times MC plus B times MC. This is the same argument as before, just starting with addition in the first pair. Okay, so with this we're done, because we've seen that a one-object AB category, R, consists of an abelian group, which we call R star star. So this is already an abelian group. And then we also have an operation, which we can interpret as a multiplication. So that's this times M that we've defined through composition with the map M. And finally, this multiplication fulfills a distributive property, so it distributes over addition on both sides. And moreover, we have a unit for the multiplication, which is a unit for multiplication on both sides. And this unit is just given by the image of the element 1 of Z under the identity map. So in fact, our one object AB category is just a ring. More generally, if we have an AB category with more objects, then each object will have a ring structure for itself. And this is given in the same way as we did this for this one object AB category. However, in the more general case, we'll also have Hom objects between objects, and these will have to be compatible in some way with the ring structures on each object. All right, so this concludes what I wanted to say on the definition of an enriched category. I hope these many examples I've given give you an idea of how encompassing this concept is. And next time, we'll be looking at morphisms between enriched categories, which are called V-functors.